Lightning strikes can generate extremely high currents, up to hundreds of thousands of amps, and voltages up to millions of volts. Concrete has a relatively low electrical conductivity, so it can offer significant resistance to the flow of lightning current. This resistance can cause the lightning current to concentrate in the steel reinforcement bars, rebar, within the concrete pile, which can lead to overheating, melting, and subsequent damage to the concrete. Stray ground currents are stray electrical currents that flow unintentionally through the ground, typically caused by electrical faults or inadequate grounding systems. These currents can enter Ufer ground electrodes and cause the rebar to corrode. The rebar in Ufer ground electrodes is typically connected to the electrical system of the building. If stray ground currents enter the Ufer ground electrode, they can flow through the rebar and back into the building's electrical system. This can cause the rebar to corrode over time, acting as a sacrificial anode. There are anecdotal reports of lightning strikes causing damage to concrete piles used as Ufer ground electrodes. However, controlled studies specifically investigating this phenomenon are lacking. There is documented evidence of stray ground currents causing corrosion of rebar in Ufer ground electrodes. For example, a study by the National Oceanic and Atmospheric Administration found that stray ground currents from a nearby power substation caused significant corrosion of rebar in a Ufer ground electrode. It's important to note that the severity of damage or corrosion will depend on various factors, such as the intensity and duration of the lightning strike, the characteristics of the concrete pile, and the presence or absence of corrosion control measures. Several factors influence the potential damage to concrete piles and rebar in Ufer grounding systems. Firstly, the intensity and duration of a lightning strike are critical. A more powerful and prolonged strike introduces a greater amount of energy into the system, escalating the risk of damage. Secondly, the composition and condition of the concrete play a significant role. Concrete with higher electrical resistance can lead to increased heat generation within the rebar. Thirdly, the presence of moisture and contaminants in the soil surrounding the Ufer ground can exacerbate corrosion caused by stray currents. Fourthly, the design and installation of the grounding system itself impact its vulnerability. Properly sized and connected grounding conductors can help to safely dissipate lightning energy and minimize the flow of stray currents through the rebar. Fifthly, the proximity to other electrical infrastructure is important. Nearby power substations or other sources of stray currents can increase the risk of corrosion. Lastly, the presence of corrosion control measures, such as coatings or cathodic protection, can help to mitigate the effects of stray currents. Mitigation strategies for lightning strikes include implementing lightning protection systems, such as lightning rods and surge arresters, which can help to divert lightning current away from the Ufer ground. Also, ensure proper grounding and bonding of all electrical equipment to minimize the potential for voltage surges. Regular inspections of the concrete piles and grounding system are essential to identify any signs of damage or corrosion. Mitigation strategies for stray ground currents include identifying and correcting the source of the stray currents and implementing proper grounding techniques to minimize the flow of stray currents through the ground. Consider using corrosion-resistant rebar or applying coatings to protect the rebar from corrosion. Cathodic protection systems can also be used to protect the rebar from corrosion. Regular monitoring of the grounding system can help to detect and address any potential problems early on. Understanding Ufer grounds can be achieved by remembering that they are a type of concrete-encased electrode, often a reinforcing bar within a concrete foundation or footing used for electrical grounding. They provide a direct connection to the earth, helping to dissipate electrical fault currents and protect against electrical shock. According to the National Electrical Code, in section 250.52, a concrete encased electrode must meet specific requirements. The electrode must consist of at least 20 feet 6.1 meters of one or more barrows in galvanized or other electrically conductive coated steel reinforcing bars or rods of not less than 1/2 inch 12.7 millimeters in diameter, or consist of at least 20 feet 6.1 meters of bare copper conductor not smaller than number 4 American wire gauge. It must be encased by at least 2 inches 50.8 millimeters of concrete and must be located within and near the bottom of a concrete foundation or footing that is in direct contact with the earth. Keep in mind that the requirements can vary based on local electrical codes and specific application needs. The principles of operation of Ufer grounds are based on providing a low impedance path for electrical currents to flow into the earth. When a fault occurs in an electrical system, the fault current flows through the grounding conductor to the Ufer ground. The Ufer ground dissipates the current into the earth, preventing voltage buildup and reducing the risk of electrical shock. The concrete encasement provides a large surface area for contact with the earth, which helps to reduce the impedance of the ground connection. The steel reinforcing bars or copper conductor provide a low resistance path for the current to flow. The overall effectiveness of a Ufer ground depends on several factors, including the size and configuration of the electrode, the conductivity of the surrounding soil, and the quality of the concrete encasement. When examining the advantages of Ufer grounds, they offer a number of benefits compared to other types of grounding electrodes. Firstly, they provide a very low impedance ground connection, which is important for safety and equipment protection. Secondly, they are relatively inexpensive to install, as they can be incorporated into the building's foundation during construction. Thirdly, they are very durable and require little maintenance. Fourthly, they are effective in a wide range of soil conditions. Potential disadvantages do exist. Firstly, they can be difficult to inspect as they are buried in the concrete foundation. Secondly, they can be susceptible to corrosion, especially in corrosive soil conditions. Thirdly, they may not be as effective in areas with very dry or rocky soil. The specific requirements for Ufer grounds are outlined in the National Electrical Code Section 250.52. 8.3. These requirements include the size and type of electrode, the depth of burial, and the connection to the building's electrical system. It is important to consult the NEC and local electrical codes to ensure that Ufer grounds are installed correctly. Regular inspection and maintenance are important to ensure that Ufer grounds continue to function properly. Inspection should include a visual examination of the concrete encasement for signs of cracking or damage. Electrical testing should also be performed to verify the impedance of the ground connection. Maintenance may include repairing any damage to the concrete encasement, tightening connections, or replacing corroded components. When dealing with corrosion prevention, it is a critical aspect of ensuring the long-term performance and reliability of Ufer ground electrodes. Corrosion can degrade the steel rebar within the concrete, increasing the resistance of the grounding system and reducing its effectiveness in dissipating fault currents. Corrosion can also lead to structural damage to the concrete foundation. Firstly, consider using corrosion-resistant rebar, such as epoxy-coated or stainless steel rebar, which can significantly reduce the risk of corrosion. Secondly, apply protective coatings to the rebar, such as epoxy coatings or zinc coatings, which can provide a barrier against moisture and corrosive elements. Thirdly, ensure proper concrete mix design and placement, which can minimize the penetration of moisture and corrosive elements into the concrete. Fourthly, implement cathodic protection systems, which can electrically protect the rebar from corrosion. Fifthly, control stray ground currents, which can accelerate corrosion of the rebar. Sixthly, perform regular inspections and maintenance to detect and address any signs of corrosion early on. Soil conditions and environmental factors significantly influence the corrosion of Ufer ground electrodes. The pH of the soil is a critical factor, as acidic soils can accelerate corrosion. The moisture content of the soil also plays a role, as moisture is necessary for corrosion to occur. The presence of chlorides, sulfates, and other corrosive elements in the soil can also increase the risk of corrosion. Temperature fluctuations can also contribute to corrosion, as they can cause expansion and contraction of the concrete and rebar, leading to cracking and damage. Firstly, conduct a soil analysis to determine the pH, moisture content, and presence of corrosive elements. Secondly, select appropriate corrosion-resistant materials based on the soil conditions. Thirdly, implement proper drainage to minimize moisture accumulation around the Ufer ground. Fourthly, consider using a sacrificial anode system to protect the rebar from corrosion. Fifthly, perform regular inspections and maintenance to detect and address any signs of corrosion early on. Stray ground currents pose a significant threat to Ufer ground electrodes, potentially accelerating corrosion and compromising their effectiveness. Stray ground currents are unintentional electrical currents that flow through the earth, often originating from faulty electrical systems, improper grounding, or nearby electrical infrastructure. Firstly, stray ground currents can cause corrosion of the rebar in Ufer ground electrodes, reducing its cross-sectional area and increasing its resistance. Secondly, stray ground currents can interfere with the operation of sensitive electronic equipment. Thirdly, stray ground currents can pose a safety hazard, as they can create a potential difference between the earth and grounded objects. Identifying sources of stray ground currents is crucial for mitigating their impact on Ufer ground electrodes. Firstly, inspect electrical systems for faulty wiring, loose connections, and improper grounding. Secondly, check for unbalanced loads in electrical circuits. Thirdly, investigate nearby electrical infrastructure, such as power substations and transmission lines. Fourthly, use ground current meters to measure the flow of current in the earth. Mitigating stray ground currents involves a multifaceted approach. Firstly, correct any faults in electrical systems that are causing the stray currents. Secondly, improve grounding systems to provide a low impedance path for fault currents to return to the source. Thirdly, install isolation transformers to prevent stray currents from entering sensitive equipment. Fourthly, use cathodic protection systems to protect Ufer ground electrodes from corrosion. Fifthly, regularly monitor ground current levels to detect and address any potential problems. In areas prone to lightning strikes, Ufer ground electrodes are particularly vulnerable to damage. Lightning strikes can generate extremely high currents that can flow through the Ufer ground, potentially causing severe damage to the concrete and rebar. Firstly, lightning strikes can cause cracking and spalling of the concrete encasement. Secondly, lightning strikes can melt or vaporize the rebar, reducing its cross-sectional area and weakening the grounding system. Thirdly, lightning strikes can damage electrical equipment connected to the grounding system. Implementing lightning protection measures is essential for safeguarding Ufer ground electrodes in lightning-prone areas. Firstly, install lightning rods to intercept lightning strikes and divert the current away from the Ufer ground. Secondly, use surge arresters to protect electrical equipment from voltage surges caused by lightning strikes. Thirdly, ensure proper grounding and bonding of all electrical equipment. Fourthly, regularly inspect the Ufer ground for any signs of damage after a lightning strike. When dealing with inspection and testing procedures, regular inspections and testing are crucial for ensuring the continued effectiveness and safety of Ufer ground electrodes. Inspections can help identify potential problems such as corrosion, damage, or loose connections, while testing can verify the impedance of the grounding system and its ability to dissipate fault current. Visual inspections should be conducted at least annually. Look for signs of cracking, spalling, or discoloration of the concrete encasement. Check for any loose or corroded connections. Measure the resistance of the grounding system using a ground resistance meter. Compare the measured resistance to the original installation value and to the requirements of the National Electrical Code. Perform continuity testing to ensure that all grounding connections are intact. Perform earth resistivity testing to assess the conductivity of the soil surrounding the Ufer ground. Testing methods for Ufer grounds include the 3-point fall of potential method, which is the most accurate method for measuring ground resistance. The clamp-on ground resistance meter method is a convenient method for measuring ground resistance without disconnecting the grounding electrode. The soil resistivity testing method is used to determine the conductivity of the soil surrounding the Ufer ground. Interpreting test results involves comparing the measured ground resistance to the requirements of the National Electrical Code. A low ground resistance indicates a good ground connection, while a high ground resistance indicates a potential problem. If the ground resistance is too high, take correct action to improve the grounding system. Corrective actions may include adding additional ground rods, improving the soil conductivity, or repairing any damaged connections. Analyzing case studies and real-world examples is beneficial for understanding the practical implications of Ufer ground electrodes. These examples can illustrate the effectiveness of Ufer grounds in various applications and highlight potential challenges and solutions. Firstly, examine a case study of a Ufer ground used in a commercial building. Analyze the design, installation, and testing of the Ufer ground. Evaluate the performance of the Ufer ground during a fault condition. Secondly, consider a real-world example of a Ufer ground that was damaged by corrosion. Investigate the causes of the corrosion and the steps taken to repair the Ufer ground. Assess the long-term performance of the repaired Ufer ground. Thirdly, analyze a case study of a Ufer ground used in a lightning-prone area. Evaluate the effectiveness of the lightning protection measures that were implemented. Assess the condition of the Ufer ground after a lightning strike. When considering common misconceptions and best practices, several misconceptions exist regarding Ufer ground electrodes, and it is important to dispel these misconceptions to ensure proper understanding and application. Firstly, there is the misconception that Ufer grounds are maintenance-free. Ufer grounds require regular inspection and testing to ensure their continued effectiveness. Secondly, there is the misconception that Ufer grounds are effective in all soil conditions. Ufer grounds may not be as effective in areas with very dry or rocky soil. Thirdly, there is the misconception that Ufer grounds are a substitute for other grounding methods. Ufer grounds should be used in conjunction with other grounding methods to provide a comprehensive grounding system. Best practices for Ufer ground installation and maintenance include following the requirements of the National Electrical Code, using corrosion-resistant materials, ensuring proper concrete mix design and placement, implementing lightning protection measures, and performing regular inspections and testing. Code compliance and safety standards are essential considerations when working with Ufer ground electrodes. The National Electrical Code provides detailed requirements for the installation and maintenance of Ufer grounds. These requirements are designed to ensure the safety of people and property. Firstly, all Ufer ground installations must comply with the requirements of the National Electrical Code. Secondly, Ufer ground installations must be inspected and approved by a qualified electrical inspector. Thirdly, workers who install and maintain Ufer grounds must be properly trained and qualified. Safety standards for working with Ufer grounds include wearing appropriate personal protective equipment such as gloves, eye protection, and safety shoes. Following safe work practices to prevent electrical shock. Ensuring that all electrical equipment is properly grounded. When examining future trends and innovations, the field of Ufer ground electrodes is constantly evolving, with new technologies and innovations emerging to improve their performance, durability, and safety. Firstly, there is the development of new corrosion-resistant materials. Researchers are developing new materials that are more resistant to corrosion, which can extend the lifespan of Ufer ground electrodes. Secondly, there is the use of nanotechnology. Nanotechnology is being used to improve the conductivity of concrete and to create more effective corrosion inhibitors. Thirdly, there is the development of smart grounding systems. Smart grounding systems use sensors and communication technologies to monitor the performance of Ufer ground electrodes and to detect potential problems early on. These innovations hold the promise of further enhancing the effectiveness and reliability of Ufer ground electrodes. The design considerations for Ufer grounds involve a comprehensive approach to ensure optimal performance and compliance with safety standards. Firstly, determine the required grounding resistance based on the electrical system's size and sensitivity. Secondly, select the appropriate size and type of grounding electrode. Thirdly, determine the optimal location for the grounding electrode, considering soil conditions and proximity to electrical equipment. Fourthly, ensure proper connection of the grounding electrode to the electrical system. Fifthly, consider the need for lightning protection and surge suppression. Sixthly, document the design and installation of the grounding system. The installation process requires careful attention to detail to ensure a reliable and effective grounding system. Firstly, prepare the soil by removing any rocks, debris, or other obstructions. Secondly, install the grounding electrode according to the manufacturer's instructions and the requirements of the National Electrical Code. Thirdly, connect the grounding electrode to the electrical system using appropriate grounding conductors and connectors. Fourthly, backfill the excavation with soil, compacting it to ensure good contact with the grounding electrode. Fifthly, test the grounding system to verify its effectiveness. Maintenance and troubleshooting are ongoing aspects of ensuring the long-term performance of Ufer grounds. Firstly, perform regular visual inspections to identify any signs of damage, corrosion, or loose connections. Secondly, test the grounding system periodically to verify its resistance and continuity. Thirdly, if any problems are detected, troubleshoot the system to identify the cause and implement corrective actions. Fourthly, keep records of all inspections, tests, and maintenance activities. Understanding common issues and resolutions is crucial for maintaining the effectiveness of Ufer ground electrodes. One common issue is corrosion, which can be addressed by using corrosion-resistant materials, applying protective coatings, and implementing cathodic protection systems. Another common issue is high ground resistance, which can be addressed by adding additional ground rods, improving soil conductivity, and repairing any damaged connections. A third common issue is loose connections, which can be addressed by tightening or replacing the connections. Proper documentation and record keeping are essential for maintaining a reliable and safe grounding system. Firstly, keep records of the design, installation, and testing of the grounding system. Secondly, document all inspections, tests, and maintenance activities. Thirdly, maintain a record of any problems that are detected and the corrective actions that are taken. Fourthly, store all documentation in a safe and accessible location. The role of Ufer grounds in electrical safety is paramount, as they provide a low impedance path for fault currents to return to the source, minimizing the risk of electrical shock and equipment damage. Ufer grounds help to maintain a stable ground potential, preventing voltage differences between grounded objects. They also help to dissipate lightning energy safely into the earth. By providing a reliable grounding system, Ufer grounds play a vital role in protecting people and property from electrical hazards. The economic considerations of Ufer grounds involve a cost-benefit analysis to determine the most cost-effective grounding solution for a particular application. Firstly, consider the initial cost of installing a Ufer ground, including materials and labor. Secondly, factor in the long-term maintenance costs, such as inspections, testing, and repairs. Thirdly, weigh the benefits of a Ufer ground, such as improved safety, reduced equipment damage, and increased reliability. Fourthly, compare the cost of a Ufer ground to the cost of other grounding methods. In many cases, Ufer grounds offer a cost-effective solution compared to other grounding methods, especially when the cost of installation can be integrated into the building's foundation construction. Therefore, understanding the principles, applications, and best practices of Ufer ground electrodes is essential for electrical engineers, contractors, and inspectors. This knowledge enables them to design, install, and maintain effective grounding systems that ensure the safety of people and property. By staying informed about the latest trends and innovations in Ufer ground technology, professionals can continuously improve the performance and reliability of grounding systems.